Hello and welcome to lesson 1 of week 3. In this lesson, we are going to look at the quicksort algorithm. My name is Mildred. Now, when we talk about this quicksort, we are talking about a divide and conquer algorithm. Now, what it does is that it chooses one value from an array and uses this value as a pivot element. Now it takes the rest of the values in that array and creates two subarrays. Every value that is less than the pivot element will be to the left of it, and every value that is greater than the pivot element will be to the right of it. And then it does this recursively with each subarray until completely sorted, and then merges all three. But the pivot, everything on the left, everything on the right, to get a complete sorting. Let's see how we implement this algorithm and see what the time complexity will be like. So let's say we have an array and I have elements, let's say 5, 3, 8, 4, 2. When we pick a pivot element, let's say we pick 4, it looks at the rest. Everything less than 4 will be in the left, everything greater than 4 right. That's two subarrays, and then it takes this left and recursively call itself. So which means that when we implement this algorithm, we are going to recursively call this algorithm back to repeat the process until the ones left on the either side is too small to be broken down or to be sorted. Now let's try to implement this. I'll create a function and I'll call this function quicksort. We want this to take an array of items, and let's call these items. The first thing we want to do, we want to make sure that we have more than one item in that array to sort. So we want to say if the length of the items is less than or equal to 1, we want to just return back the array without doing anything further. So return back the items, all right? But if not, we want to start looking at it. Now, how do we select a pivot item? You can pick anything as a pivot. You can pick the first, the last, the middle, anything. But for this algorithm, I will write it so that it looks for the middle item. Right, so let's say pivot will now be equal to, we want to get the middle of it. So let's say it will be like the items, we want to get the length of the items, right? So we want to get items and we want to get the middle of the length. So say length of items divided by 2. So we use the floor operator here, which will give us round to the nearest whole number. So in case if we have odd numbers and divide and we get something point something, it gives us the nearest and picks something just close to the middle. So this is the same thing as saying n is equal to here to say n is equal to length of the items. Okay, and then when you come here, you say if n is less than or equal to 1, and here to make it easy to get the item at a particular index, we want to get at the middle index, so we say n divided by 2, but we use this to round to the nearest integer. Okay, so we get the pivot item to be the item at the middle index when we compute this. Then we want to now say when it takes this pivot, everything less than this pivot should be in an array, and we'll call this array, let's just call it left, right? And for this left, we want to get everything less than the pivot item. So we can use list comprehension to say x for x in items if x is less than the pivot. Okay, so we're just saying that for this left, we're just looping, and if the x now is like the iterator, we want to say if it is less than the pivot item when it loops through the items, and if of every iteration on the loop, if the value of that item is less than the pivot, you want to store it in left, right? So we have a list called left. We want to have another subarray, right? And this will be the middle one. This is going to be where the pivot is stored. So this one is going to be, we'll do the same thing, x for x in array if x is equal to the pivot. So we'll label this as the middle item, and then we want to get the right one now to be equal to x in. So now we're doing array, but it's items we are using, right? The name of the parameter is item, so we use items. So x for x in items if this. Okay, I'm using array because of this, but we're not using it yet, we're just creating the variables. So we'll say x for x in items if x is greater than the pivot. So this is the algorithm that we said. We get the pivot item, we just did something to just make it the middle item or something close to the middle, and then we now create two subarrays, one to the left of the pivot and the other to the right. Everything to the left of the pivot is less than the pivot, everything to the right is greater than the pivot, and we say the pivot is the middle item. So we created three variables, left, middle and right, because we are going to add them together. Now when we want to return, because we are doing this recursively, in our return statement now we are going to do all this function within itself. So we'll say quicksort, and we want to repeat this on the left, right, and then we want to add the middle to the list, middle, and then we also want to run the quicksort on the right. So we'll check this to see if it's correct, then I'll explain it again. So what we are doing here is to get that pivot, everything less than it to the left, everything greater than it to the right, and we keep the pivot as the middle. And when we want to return, because we are doing this recursively, it's just easier to say call the quicksort to the quicksort again on the left and to the quicksort again on the right. So we're returning this like this. So let's see if this works, and then we will explain. So say if name, so we're going to print this, and when I run this we have it sorted. And so this is how the quicksort works. So this method I use is short. We have other method where you can say you want to have an empty array called, or an empty list called left, like this, and you say left is equal to an empty list, then you want to get the right is equal to an empty list, then you append, you compare. When you loop through for I in maybe the range, the length of the items, you loop through. If the value held there at the ith index is less than the pivot, append to the left. If not, append to the right, and then you now return quicksort. So it's just the same thing, but using this is faster. Okay, so a lesson resource would give you two different ways of doing the same thing. So let's think about this carefully and see what the time complexity is like. For the worst case, like we see this, the time complexity might be n squared. And that worst case will occur if the pivot is maybe the smallest item or the most extensive one. So if you have like the smallest item and you have an already sorted array and you have a bad pivot, that's the worst case. At this point, you will now have your time complexity to be n squared. But if you don't have it that way, then you now have your best case to be when you have good even split, okay, and your average case also the same as the best case. So we taking note of the worst case. This is n squared, which makes it similar to the worst case of all the other algorithms that we have looked at previously. In the next lesson, we are going to look at the counting sort algorithm. Thank you, and see you in the next lesson.